What I will represent here on the blackboard is an array composed of n telescopes. And the telescopes can have any kind of shape. So I just draw them as if they were banana. Okay. I only drew a limited number of these, but in fact their number can be n. So n apertures. Well, a single aperture, I may represent it as A0, xy. So this is the distribution of the complex amplitude, in the pupil of a single telescope. And now what I would like, is to represent, what is the complex amplitude, of the whole array. Okay, so, well, let's draw in blue, so that it's nicer. The array of n apertures. And now I would like to express, the distribution of the complex amplitude, in this pupil plane, which is quite complex, So I say, okay, it is the summation of small n equal 0. I start with 0. You will understand why in a moment, to n minus 1. So I have a summation of n elements, Of what? Well, I can write of A0 times x. And now I say plus n minus 1 times A over 2. Now, A is the distance between two consecutive elements. Okay? And now I make minus n times A. So I pretend that this describes the distribution of the complex amplitude in this pupil plane. So how many elements do I have here? You agree I have 6 elements. Okay. 6 elements. Now let's try to see whether this is okay or not. So I remind you, that A0 of xy would in fact indicate the position of one such element centered on x equals 0. So this would be A0 of xy. But well, I have the same elements which have been translated. So I try to represent them here. Now, do you agree that the position x of one such element will be given by x is equal to, in fact, NA, just the opposite sign of that number, minus n minus 1 times A over 2. Okay, let's try to see. For n equals 0, it means that x is equal minus n minus 1 times A over 2. If n is equal 6, this will be minus 5 half times A, so minus 2.5 times A. And indeed, this is minus 1 half, minus 1.5, minus 2.5. So I'm here. This is n equals 0. And after what I do, well, I just add NA. So n equals 0, it's here. 1A, 2A, 3A, 4A, 5A, which is n minus 1, big N minus 1. So you may check at home that this is a correct representation of the distribution of the complex amplitude in the pupil plane. Now, okay, what I do, I say, okay, the amplitude in the focal plane of such an interferometer, I know by the fundamental theorem, is a Fourier transform, of A xy, which depends on the variables P and Q. Okay, the Fourier transform of this quantity will be the summation of the Fourier transform of each individual quantity. So I may write this will be equal to the summation of n equals 0 to n minus 1 times the Fourier transform of A0 Well, here I forgot something. I forgot to write comma y. Yeah, you always forget something. Yeah. So a0 of x plus n minus 1 times a half minus n times a comma y. PQ. You agree? Don't hesitate, yeah, if you have a doubt. No? Okay. Now here we see that this argument, yeah, represents a kind of translation of the complex amplitude, yeah. So I will make use, yeah, of the translation property of the Fourier transform, yeah. So I may rewrite this as being equal to summation of n equals 0 to n minus 1. Now, you remember it will be the exponentiation of I to pi multiplied by n minus 1 times a divided by 2 minus n times a, like that, times p, the variable p. Now I close the parenthesis, n of a0 xy of the Fourier transform of a0 xy pq. Yeah. So it's just the application of the translation property of the Fourier transform. Yeah. Okay, now I see that when I make the summation over small n, this does not depend on small n, only this depends on small n. So I may rewrite the result as follows. It will be equal to the exponentiation of I to pi times n minus 1 times a over 2 times p. So the 2 here and the 2 here simplify, multiplied by the summation of n equals 0 to n minus 1 of exponentiation of minus, okay, minus what? I to pi times n ap. Do you agree with that? Times the Fourier transform of a0 xy of pq. Now I would like to simplify this, and I will just remind you here a result that summation of n equals 0 to n minus 1 z exponent n. So this is equal to 1 plus z square plus z n minus 1. And this is simply equal to, well, z exponent n minus 1 divided by z minus 1. Yeah. So you may check this result. Yeah. It's easy. So this comes equal to exponentiation of I pi n ap, like that, divided by exponentiation of I pi ap multiplied by, now here I will have exponentiation of minus I 2 pi n ap minus 1 divided by exponentiation of minus I 2 pi times ap minus 1. Yeah. Now it's easy to distribute this factor onto these two terms. I will get then that it's exponentiation of minus I pi n ap minus 1 divided by exponentiation of minus I pi AP minus 1. Yes? Oh, no. I forgot to distribute on this term too. Yeah? So minus exponentiation of IP n AP minus exponentiation of IP AP. Now it's correct. Yeah? Now I see that the subtraction of these two terms, yeah, will give me, yeah, minus 2i sine divided by minus 2i sine, etc., etc. Yeah? So here what I will get is that it will be the sine of pi n AP divided by the sine of pi times AP. Yeah? And now, well, I have to multiply, yeah, by the Fourier transform of A0 xy PQ, and here also multiply by the Fourier transform of A0 xy of PQ. Okay, now, so this is expression of APQ. What we are really interested in, yeah, is the intensity in the focal plane, yeah, because you can only measure intensity distributions and not amplitude distributions. So IPQ is the square of what I've obtained here, so it's easy. Now I will particularize, yeah, these two, the case of a square aperture, yeah. So you remember, well, I have to take the square of that, yeah, and so it would be 2 times. So this is A, okay. So it was 2 times d square at the power 2, yeah, times the sine pi p d over pi pd square times the sine of pi qd square, like that. And now you will take the square of this, yeah? So now, here it was 1. It's for 1 square aperture, yeah? Yeah, not 2, 1. And now we multiply by the square of that, yeah? So it will be the sine of pi n AP square, and here sine pi AP square, like that. Now I do the following. I divide here, yeah, by pi AP square. So I multiply here by pi AP square. Now I still divide here by n square. So here I have to put an n. Okay? And this finally is the expression, yeah, I obtained for the intensity distribution in case I use an interferometer composed of n elements, yeah. Well, in this case, square apertures, yeah. Now I will show on a diagram, yeah, how the intensity distribution will look like. So essentially along the p direction, yeah. So this is the p direction. Here I represent the I, well, of PQ, and the Q would go like that. So it would be something like that, yeah? When P equals 0, Q equals 0, this is 1. This is 1. This is 1. This is 1, yeah? So what remains is a nd square at the power 2, yeah? So it's the square, in fact, yeah, of the total surface of the array, yeah? So more you have elements, yeah, well, you will have a better sensitivity. So, okay, this maximum value, yeah, will be n d square at the power 2. Now, in fact, this will be the square of sine, cardinal, yeah, going like that. And now I'm interested, yeah, by the weights, yeah, of the central element, yeah, which will define the angular resolution of my interferometer, yeah. Now, I know that this minimum here will occur when in the sign I will have a pi argument and here minus pi, which means that whenever pi n ap is equal to plus or minus pi, I will have a 0 value, yeah, and this will provide me, yeah, the way to define the angular resolution of my interferometer. So I find here that P is equal to plus or minus 1 over n times A. But P, I remind you that it is equal to x prime over f times 1 over lambda. So I have here that first delta P is equal, as before, yeah, 2 divided by NA. And therefore, delta x prime over f is equal to 2 times lambda over NA. And well, this is the angular resolution, yeah, of my interferometer, yeah. So it's proportional to the wavelength and divided, yeah, by the total length of my interferometer, n times A. Yeah. Okay? So this defines the angular resolution of my interferometer. Now I see that I should account, yeah, so I have already accounted, yeah, for this dependence, yeah. Okay. Now I would like to account for this one. Well, this one it's easy. It's also a sinc function, something going like that. And this is in fact the response function due to a single square aperture. Yeah. But now in addition, yeah, well, this is along the q direction, yeah, which means that along the q direction I have no interference, yeah, but I also have this very broad peak. But now this is an interesting quantity, yeah, because I see that whenever this is equal to 0, well, there is a peak, yeah. So whenever pi AP, so pi AP is equal to pi, so it means whenever P is equal to 1 over A, so maybe here I will have 1 over A, 2 over A, 3 over A. Here, well, I will have something like that, yeah. Secondary peaks, yeah. Secondary peaks, yeah. And well, this, if you would take, yeah, the power spectrum, yeah, of this intensity, you would see that this gives rise, yeah, to information, yeah, at different spatial frequencies, yeah, due to the spacing between two interferometers, yeah. Okay, so that's the end of the demonstration. So it's not difficult, yeah. You've seen that I'm just applying, yeah, Fourier transform properties. Yeah. Now I come back here to one of the last view graphs. This one. So you see, this was the array we have considered, yeah, and this is, yeah, the response function that I've drawn, yeah, on the blackboard. And what we have established here for the case of an optical interferometry would be valid for a radio interferometer. It's the same. So in particular, yeah, well, these are diagram antenna, yeah. And now comes the ideas of the projects for the students, yeah, yeah, okay. So the idea is that first part, yeah, you consider an array where the apertures can be either square apertures or they could be also circular apertures. Yeah? And you may either observe a star at the zenith, but you also could observe a star, which is slightly inclined along the line of sight, as it would occur, with a with a optical interferometer, And the unit vector, indicating the orientation of the star, is b over f c over f1. So remember, we have addressed that problem, for a single aperture, assuming that the star was not at the zenith but was oriented along a different angle of view. Then after, what you could do, now you could orient, all your individual elements in the direction, of that star, Then what would happen, in fact, Do you agree that the star, sees this array as something like that, It sees its projection, So the baselines are not the same anymore, There is a cosine, which enters, and then there are delays, for which you have to bring a correction, And afterwards, the third case, is that you could consider that the telescopes are oriented along that direction, but the star is oriented along another direction, and see what happens. So I said for the case of a square aperture or the case of a circular aperture, So it's very simple. So using a Python program, just to make something, individual, and then we interact by email,